Okay, there are a few people at YouTube, but I think we'll wait for a couple of minutes. People are still joining. Where did I use that? Yeah. Snigdha, shall we start?
Yeah, I think people are joining, but now most of the people have joined. I think many people have joined, so we can start the meeting.
Okay. Good evening and welcome to this IPA colloquium. Let me just introduce IPA briefly because some of you may not know about it. I am Vandana Nanal, General Secretary of Indian Physics Association. IPA was founded in 1970, basically with a goal to help the advancement and dissemination as well as applications of knowledge of physics. This is achieved through various publications and arranging seminars, lectures, and special programs, mainly for students and teachers and young researchers. So here you can briefly have a quick overview of various chapters of IPA. The activities are spread all over India, and we look forward to ISER Bhopal playing a role in the making the IPA chapters in this region active and engage with IPA. So at the outset, I would like to thank ISER Bhopal for holding this lecture. So IPA organizes many lectures like a DAE CV Raman lecture series. There are 5 lectures by eminent scientists. It liaises with the international societies like APS, American Physical Society, Institute of Physics UK, and recently we have also signed an MOU with Italian Physical Society, and IPA is a member of Association of Asia Pacific Physical Societies. The reason I mention this is because of the intersocietal agreements. The IPA members have similar privileges in many cases for many conferences, publications as these sister organization members. So it's also a kind of good bonus for the IPA members. In addition to the lecture series, the IPA brings out a quarterly bulletin, Physics News, which is available online now for last couple of years. And I would urge all of you to visit the IPA webpage and browse this recent issues. So this was one of the special issue which was brought out in the 2021. This featured the life and science of Dr. Bibha Chaudhary, one of the first woman high energy physicists of the country. And IPA gives awards to senior and young scientists in recognition of their contributions to the physics. These are the current office bearers. The present president of IPA is Professor Ramakrishnan, Director TIFR. Vice President is Professor Tanushree Sahadas Gupta, Director SN Bose Center. Myself, General Secretary. Professor Samit Mandal, Delhi University Joint Secretary. Dr. Aradhana Srivastava from NPD is Treasurer. And IPA established a gender in physics working group few years back, and Professor Shubhavati Goswami from PRL is the chair of the IPA gender group. And for more activities, you please visit our webpage. I will also put the address in the chat box. I don't want to go into detail right now to delay the main event. So IPA Colloquium Series was started in April 2021 after the successful completion of IPA 50, which was the first online major event which we organized due to the pandemic. And this is one of the sort of fallouts of the pandemic, is that because of the online events, we have been able to reach and organize events at wider community and at remote places in India as well. So the first half of this year, we had special colloquia on innovative technology and applications, and most of these lectures are available on the IPA YouTube channel. Recently, IPA also partnered with UPES in the outreach programs for the school students. And in this series, lecture series today, we are very happy to have Professor Bedanga Mohanty, who recently was awarded Infosys Prize for Physical Sciences. And now I will invite your host, Dr. Snigdha Thakur, the head of the physics department in ISER Bhopal, to take over. Thank you.
Thank you, Professor Vanna. So I'll take up this opportunity to introduce ISER Bhopal to all of you. Of course, many of the people in the seminar right now are from ISER Bhopal, but there is a substantial number is not for ISER Bhopal. For them, I would quickly like to tell you about ISER Bhopal, maybe in next 2-3 minutes, and then we can go to today's colloquium. And so I'll not take too much time. So I'll just introduce ISER Bhopal to all of you. So ISER Bhopal was established by Government of India, along with all other ISERs and NISERs, and the basic idea is to promote the science in India. So ISER Bhopal came into picture somewhere in 2008, and the first ISER to establish in this context was ISER Pune and Kolkata, which was 2007. And you can see NISER, the speaker from today is from NISER, and NISER is our sister institute, which was also established along the same time when the ISER Bhopal and Trivandrum had come into picture. So just to give you a glance of ISER Bhopal, so we have right now 10 departments, 5 in science, and then there are other departments in engineering, also in humanities and social sciences. And in all these departments, we have UG programs, we have a BSMS program in all the natural sciences department, and BS program in engineering sciences and economics HSS department. And of course, PhD and IPhD program is running in all other departments as well. So, with that, I would also like to highlight that ISER Bhopal is doing quite well since a few years after the establishment. And we can see it coming up in all the rankings, that be it international or national, and we are featuring in all the ranking that shows that we are doing well, and I think we have to do better now to go even higher in the ranking from where we are right now, and we will strive for that for sure. With that, just to give you a glimpse of Department of Physics, where we are hosting this colloquium today, we have a substantially big department with around 25 to 30 faculty members. And roughly 150 UG students and around 100 PhD and IPhD students. So it's a substantially big department where people are working in all the areas, many of the areas of physics that you can think of, starting from high energy to condensed matter theory, experiments. There are various areas, thirst areas that I have highlighted here that people are working on. And it's a very vibrant department, and after the COVID goes, I would request people to definitely visit ISER Bhopal and give us a physical lecture here. That would really be a real nice interaction that we can have after the COVID. So with that, without any further ado, I would request Dr. Navamita Banerjee to now introduce the speaker so that we can move to the actual colloquium for today. Navamita, please.
Thank you, Snigdha. for introducing our ISER Bhopal, and thank you, Vandana. So I take this opportunity to introduce Professor Mohanty to all of you. It's really a pleasure and honor for me to do this. So Professor Mohanty currently is at NICER and he's there from 2012. He did his master's and BSc from Cuttack, and then he continued his PhDs from IOP Bhubaneswar. After that, he moved to Wake for a certain time, and then he again went to US for advanced studies, particularly in Berkeley and Brookhaven National Laboratory. And during this period, he had been associated with the STAR experiment, in fact, with distinct major responsibilities, such that being group convener, physics analysis coordinator, to being the deputy spokesperson for STAR. And he is also one of the editorial board member for Large Hadron Collider experiments at CERN. So let me now just very, very briefly, maybe in 30 seconds, tell you his major contributions to experimental high energy physics that I have understood. So his primary contribution was actually the discovery of quark-gluon plasma at laboratory, and then establishing quark and hadron transition, and then comparison between the experimental heavy ion collision data with theoretical QCD, which is one of his major contributing areas. He also contributed highly in the search of QCD critical point and QCD phase transitions in RIC experiments. And he is one of the major contributors in Indian detector physics. So that is his. I think Professor Mohanty will tell us more about QGP, so I'll not talk about that. He is recipient of numerous awards, starting from all Young Scientist Awards. He's fellow of INSA, IAS, and American Physical Society. And he also has Sharna Jayanti, Bhatnagar, J.C. Bose Fellowship. And as Professor Nadal said, recently he got 2021 Infosys Prize. So let me not waste any further time and learn more about QGP from Professor Mohanty. Professor Mohanty, over to you.
Yeah, thank you very much for this kind introduction. And so let me slowly start sharing. So I would like to thank Indian Physics Association for giving this opportunity, and also all the colleagues at Indian Institute of Science, Education and Research, Bhopal, for organizing this. My sincere thanks. So the title of the talk is Quark-Gluon Plasma, the perfect and the most vertical fluid. These two properties is what I intend to discuss during this talk. So I'll start with a note which came out in Physics Today in 2000 by Frank Wilczek. Frank Wilczek got a Nobel Prize in Physics in 2004 for contributions to the theory of strong interactions, which is quantum chromodynamics. And in this article, which was in 2000, is the time where our experiments just started taking data at the Relativistic Heavy Ion Collider, the STAR experiment. And in this paper, he had our event display, which is shown on the left-hand side. This is the tracks, the lines that you see are charged particles passing through the detector. The detector is called as the time projection chamber. In that article, he wrote, in the quest for evidence of quark-gluon plasma, there are two levels to which one might aspire. At the first level, one might hope to observe the phenomena that are very difficult to explain from hadronic or normal matter perspective, but have a simple qualitative explanation based on quarks and gluons. I think that has been achieved at both RIC and the Large Hadron Collider facility. But there is a second, more rigorous level that remains a challenge for the future. Using fundamental aspects of QCD theory, one can make quantitative prediction for emission of various kinds of hard radiations from quark-gluon plasma. we will not have done justice to the concept of weakly interacting plasma of quarks and gluons until some of the predictions are confirmed by the experiment. He actually wrote in 2000, he was expecting a weakly interacting quark-gluon plasma. What turned out is a strongly coupled system of quarks and gluons. And that's how the perfect liquid nomenclature got back to quark-gluon plasma. So I will discuss about that also. So let me start with what we all know, the fundamental constituents of visible matter and the fundamental forces. In this middle part, the fundamental constituents that we know of visible matter are listed. There are a set of quarks, set of leptons, and then there are these force carriers, gluon, photon, Z and W bosons. On 4th July 2012, the Higgs boson got discovered. As a consequence, we now know how these fundamental particles got their masses. Now, these quarks are actually confined inside particles, which are generally termed as hadrons. A set of hadrons, as an example, is shown on this right-hand side. On the top 4 are what are called baryons. They have 3 quarks or antiquarks. On the below, so examples are proton, neutron, or a lambda. And below are what are called mesons. They have quark and an antiquark. Both baryons and mesons together constitute what is called as hadrons. Now, there are a set of fundamental interactions. These are listed below. One is the strong interaction. Here, this is the interaction which is responsible for holding together these quarks inside hadrons. It is also the force which is responsible to bind nucleons, protons and neutrons to form nucleus. And the theory of strong interaction is called as quantum chromodynamics. Chromo means color, because the particles which undergo this interaction are quarks and gluons, which carry this quantum number called color charge. About 100 times weaker in strength is electromagnetic interactions. The underlying theory is quantum electrodynamics. The interactions happens between electric charge carrying particles. Now, this is a force, for example, responsible for binding the electrons and the positively charged nucleus to form atoms. About 1,000,000 times weaker compared to strong interactions is the weak force, which is responsible for radioactivity. The fact that it is weak, we do not have a radioactive environment everywhere. The weakest among the 4 interactions, although difficult to sort of visualize, is the gravitational interaction, which is about 10 to the power 40 times weaker compared to strong interaction. Yet, it is the interaction which is responsible for us to be walking, the Earth moving around sun, or the moon moving around Earth. So these are the fundamental constituents and the forces. During this talk, I will be using units such as MeV, which are related to temperature scales like Kelvin or mass scales. And most of the time, you will come across systems which are at the level of an angstrom or a Fermi. The 10 to the power minus 15 is what constitutes a meter constitutes a Fermi. So that is the scales which we will be dealing with. Now let's look a closer look at the structure of an atom. We all know that atom has electrons which are moving around the positively charged nucleus. This was the picture which was given by Rutherford based on the data taken by his students. This is alpha particles getting bombarded on gold foil. Subsequently, people figured out that the positively charged nucleus are made up of neutrons and protons. And then again, repeating sort of similar scattering experiment, high energy electron on a proton target, told us that the proton has substructures, and the smallest units till date are quarks. These quarks and the intermediate binding particles, the gluons, are always confined inside hadrons, like particles like protons, neutrons. Free quarks are not seen in nature. So if somebody wants to study the properties of these systems, then it is a little bit difficult. If you have a set of free quarks and gluons, then you can try to understand the properties of this system, the particles which make all the visible matter. So is there a place or time when such quarks and gluons, free state of quarks and gluons, were found or are found? There are two such places. One is what happened way back in time. One is quite far away from all of us. So let me first discuss the situation which was very early in time. On the left-hand side is a typical time evolution of our universe. This is based on the Big Bang model. One may ask that why should one take this model as a realistic picture? That is because it made some predictions which has been verified. Some of them are, for example, the velocities of galaxies as a function of the distance of separation. It followed an increasing pattern, which is referred to as the Hubble's law. This was verified. They also told us about relative abundances of nuclei in the current time. That was also verified. And it also told us that one should expect this cosmic microwave background radiations as like Planck blackbody radiations, and those were also measured. So this picture of evolution of universe, if you see in the box below, there are time increasing, and as the universe is expanding, the temperatures falling. So if you concentrate between this band where it is about a microsecond old, 10 to the minus 10 to 10 to the minus 4, so 10 to the minus 6 second old universe. And if you note, the temperatures are 10 to the power 12 to 15 Kelvin. That is the phase where we had a free state of quarks and gluons, which we called as, or a deconfined state of quarks and gluons, which we called as quark-gluon plasma. Subsequently, these quarks and gluons formed hadrons, and then we formed the nucleus, the atom, and things evolved. So at early universe, when temperatures were of the order of 10 to the power 12 Kelvin, such a state existed. Another place where people believe, and some recent data suggests, is such a system exists in cores of neutron stars. Now, the stars, which are quite massive compared to sun, they, towards the end of their lifetime, undergo supernova explosion. The core collapses and it becomes a very dense system, so dense that even protons, electrons could form neutrons, and we have this neutron star. Now it's so dense, typical densities could be as large as 10 to the power 18 kg per meter cube. It is such a dense object that the quarks and gluons which are present in these neutrons do not know to which parent they belong. So you have a free system of quarks and gluons. So these were some of the places where one expects this system to exist or had existed. Question is, can we create such a system in laboratory? By doing so, then we can study its properties. Let's see if there is some theoretical support towards achieving this system of free state of quarks and gluons. Remember that what we see in nature, these quarks and gluons are always confined inside hadrons. Now, if one looks at the potential which leads to this confinement, so it has such expression as is shown in the middle panel. So it has something like a Coulombic term, and then there is a linear term. This is, for example, if a potential between two heavy quarks separated by a distance r. This linear term gives rise to the confinement. If one plots this potential as a function of distance of separation, this black line shows how it increases as you increase the distance. This plot in the middle is a very early calculations where they tried to see what happens to this potential if one increases the temperature. Some temperature Tc in this calculation was taken as close to 170 mega electron volt. As you increase, you can see go from the green to the red, and you see that this confining term vanishes. As a result, you can, if you go to high temperatures, you can have a free system of quarks and gluons. So this is what these calculations tell us. You can also do other calculation as shown on the right hand side. These are calculations of first principle calculations of quantum chromodynamics on lattice. What is plotted here in the y-axis on the right hand side plot is energy density divided by temperature to the power 4 as a function of temperature divided by some critical temperature. Now 1 means T equal to Tc, and then it is above. 3 means 3 times this critical temperature. What one finds is there is a sharp sort of increase and then a larger value. Goes from a smaller value and then there is an increase at T equal to Tc, and then it takes a larger value. If one uses statistical physics for a thermal system, one can show that this quantity goes as the degrees of freedom the system has times a constant. So it seems the y-axis can now be interpreted as system goes from small degrees of freedom to large degrees of freedom. Small degrees of freedom, for example, hadrons. Suppose you have a system of pions. There are 3 kinds of pion. Effective degrees of freedom is 3. But if you have a system of free quarks and gluons, it can be very large. It can be of the order of 47. So what this tells, again, this first principle QCD calculation tells that if you increase temperature of the matter, then you will make a transition from a state where quarks and gluons are confined, not free, to a state where the relevant degrees of freedom are quarks and gluons, or you can form quark-gluon plasma. And the temperature required nowadays, the calculations suggest, is about 150 MeV, which is 10 to the power 12 Kelvin. Remember, it is of the same order as the microsecond-old universe. Now, question is, can we melt matter by heating it to 10 to the power 12 Kelvin? And how can we do it in the laboratory? So we need to take matter and somehow heat it by trillion kelvins or so. So the idea came up that if we collide 2 heavy ions, such as lead or lead ions 2 or gold ions at very high energy, what happens is we pump in a large amount of energy in a small volume, leads to a large energy density, and that would lead to high temperatures, and matter would melt into its constituents, quarks and gluons, and you can form a quark-gluon plasma. So there are 2 dedicated facilities which are currently operational and which have done these experiments. One is the Relativistic Heavy Ion Collider. This is the Google map of the collider facility with a circumference of about 3.5 kilometers. They collide basically gold ions on gold ions, and maximum center of mass energy is 200 giga electron volts per nucleon. Then there is this Large Hadron Collider facility at CERN, and it has a circumference of about 27 kilometers. They dominantly collide lead ions on lead ions, and a center of mass energy is 5.5, roughly 5 tera electron volt per nucleons. And by pumping in large amount of energy in a small region, increasing the temperature, we melt the matter into its fundamental constituents, the quarks and gluons, thereby allowing us to study its properties. Now, when these collisions happen, how does the system evolve with time? This is what I discuss in this slide. First, on the left-hand side, I tried to put this evolution in terms of a Minkowski space-time diagram. X-axis is the space coordinate, y-axis is the time. Two nuclei, A and B, come and collide. Let's concentrate on the right-hand side. After some interactions, we expect that large temperatures are reached, matter melted into its fundamental constituents, the quarks and gluons. The system, then what happens is cools. And as the system is expanding, it is cooling. A temperature is reached when this free state of quarks and gluons cannot exist, and it has to go back to what we see in nature, confined state of hadrons. Now, if it's a first order phase transition, like we see in water, ice, vapor systems, then it has to go through a mixed phase, where temperature remains constant and the latent heat is used to convert the quark and gluons to hadrons. Hadronic degrees of freedom are what is left at the end of the mixed phase. The system now further expands and cools. The hadrons, the particles like pions, kaons, protons are called hadrons. They continue to interact. When the inelastic collisions stop, that is what in our field we call it as chemical freeze out, no new particles get formed. And when elastic collisions also stop, then they finally freeze out, become free streaming and hit the detector. We generally compare heavy ion collision data to proton-proton collision data. You can similarly follow the trajectory on the left-hand side without a QGP. And then you can compare the two systems' result to infer if quark-gluon plasma has been formed. That is how the basic picture goes in the experiments. On the right-hand side, again, shown is this same time evolution in a scale, just to give you an idea how long the system stays. Two spherical sized nuclei, when accelerated at relativistic speed, are Lorentz contracted. They come and collide, high energy density, matter melts into quark-gluon plasma, system cools down to form hadrons, then interactions stop, they freeze out and hit the detector. Up to this freeze out point, it is of the order of time is of the order of femtometer per C. That is, it is very short-lived. And hence it is very challenging to detect. By the way, universe undertook several transitions. This is one transition which can be directly probed in experiments because its temperature scales are reachable in the current colliders. Others can be probed through indirect ways, but this is one we are lucky to probe this QCD transition, free state of quark and gluons to a confined state of quark and gluons through accelerators, present-day accelerators, as they can reach such temperature scales. Now, one note on the detectors. Remember, we are dealing with systems which are femtoscale both in time and space, but the detectors are few meters. That is sort of an irony. They are typical detectors like the one I'm showing here from the ALICE experiment are 26 meter long, 16 meter high, 16 meter wide, several thousand tons of weight to detect this femtoscale systems. You can see here on the left-hand side is a time projection chamber, and there is a person sitting there giving you a scale idea about the scale. On the right-hand side, there are a several set of detectors. Remember, we detect almost all these particles which are coming out of the collision of two heavy ions. They vary in their nature of interactions, the charge they carry, their mass, and hence you need proper detection techniques to detect them. So we have detectors. I will not go into details of it, but time projection chamber, the 0-degree calorimeter, which characterizes sort of the impact parameter of the collision, the transition radiation detector helps identifying the electrons which come out. Then there are the cosmic detectors, the muon spectrometers where Indian group contributed. There is this photon spectrometer which measures the photons. There are the forward multiplicity detectors, the photon multiplicity detector being an Indian group contribution there, and time of flight to identify the particles which are coming out. A whole set of detectors put together based on different principles and to do this complex experiment. So those were the typical detectors. Now let me try to give you a result which will show that we have reached temperatures of the order of 10 to the power 12 kelvins. So the matter has melted into its fundamental constituents. Now, how do we measure temperature? At such temperatures, the matter itself has melted, so no ordinary sensors would work. So we take hold of statistical physics in order to get the temperature. We know for a thermal system, if you plot the energy of the constituent particles in the system versus its frequency or counts or population, then it would follow a Maxwell-Boltzmann distribution where the slope of this distribution will give you an idea of temperature. Now the question is, which set of particles that come out from our system would faithfully tell us this initial temperatures which are created so that we know if we have melted matter to its fundamental constituent. So we thought that the best candidate are photons because they only undertake electromagnetic interactions. Ours is a strong interaction system, so they will carry faithfully the information of the system, and if we measure them, then they will ideally give us the temperature. But which photons should we measure? We want to capture the photons which have come from interactions of quarks and gluons, photons from decay of hadrons like neutral pions or eta mesons has to be found out and removed from the inclusive photon data. So that takes a lot of effort to remove those and isolate and get photons coming from interactions of quarks and gluons. So what is shown on the right-hand side is the counts on the y-axis and momentum of these photons and the x-axis for two systems, the heavy ion, that is gold and gold ion collisions, photons produced in those collisions, the upper curve, and the lower curve is the reference, which is nucleon-nucleon collisions. And the lines that you see for the lower curves are calculations from theory, and the data and theory match pretty well. So we understand such photon productions in our reference system. If heavy ion or gold and gold collision was a simple superposition of proton-proton collisions, we would have expected this dashed line on the top curve. But we see excess. Those excess are evidence of photons coming from quark and gluons interacting in the QGP. It has an exponential shape. These are thermal in nature, and the slope, when interpreted, gives a temperature of the order of 300 to 600 MeV. Remember, first principle QCD calculation suggests a transition temperature of 150 MeV. These are much beyond that. We have reached temperatures of the order of 10 to the power 12 Kelvin. Matter has melted into a system, a free system of quarks and gluons or quark-gluon plasma. Now that we have reached those temperatures and quark-gluon plasma is formed, there are several other signatures which I'm not discussing here. Many many experiments simultaneously have verified these results. A host of different observables, which I will not be discussing today, including suppression of JEPSI, a particular kind of particles, strangeness enhancement, jet quenching, which has led to this conclusion. We have formed a free system of quarks and gluons. Just to give you a perspective of the temperature, these are the temperatures which are sort of lowest recorded in the laboratory. If you have a trapped ion systems, one reaches microkelvin temperature scales. 2.7 Kelvin is the universe temperature. 300 Kelvin is the temperature in the room which we all are sitting roughly. The temperatures from the core to the surface of the sun can be a maximum of the order of 1,000,000 Kelvin. If there are thermonuclear explosions, then it would be of the order of 10 to the power 9 Kelvin. And what we have reached at this nucleus-nucleus collisions are one of the largest temperatures attained in the laboratory system. It stays for a short time. So yeah, and it's of the order of 10 to the power 12 Kelvin, where matter melted into its fundamental constituents, quarks and gluons. Now we are set to study its properties. The first property that I will discuss is related to its fluidity. The measure of how nicely a fluid flows is through viscosity, because viscosity is just resistance to flow. Less is the viscosity, more free flowing is the fluid. We have all read this definition of viscosity: force per unit area is proportional to the gradient, velocity gradient of the flow of the fluids, and the constant of proportionality is viscosity. But usually one removes the density effect in order to compare the viscosity of different fluids. That's why one uses what is called as kinematic viscosity. So you divide by densities to compare kinematic viscosities to understand the fluidity of different fluids. On the right-hand side is one experiment. You can check in this wiki. There is a pitch which is kept in this container, and it is very viscous. It is, some say that it is 230 billion times viscous than water. And you can see there is a beaker below, and people are trying to find out how long it takes for one drop to fall into it. Since 1927, it has been going on, and people say that there are only 8 drops which have fallen. Many tried to see the exact time of the drop falling, but has been unsuccessful. But nowadays, with CCTV cameras and things, it could be recorded. But that is how viscous it is. It really takes years for one drop to fall into this beaker. That is one extreme. Is there a lower limit to the kinematic viscosity a fluid can have? Well, Maxwell in his derivation said that a dilute gas can have a eta, the shear viscosity given as 1/3 times number density momentum times the mean free path. Using uncertainty principle and trying to take away the density effect by dividing it with entropy density, you can see that the eta by S, just from uncertainty principle, will have some bound. That is some bound, lower bound of what viscosity, kinematic viscosity a fluid can have. More sophisticated calculations using string theoretical ideas have led to that bound of 1/4 pi. Of course, there are discussions and corrections to this, but this is typically the values which, if lowest values of eta by S, a fluid can reach. So we have formed this quark-gluon plasma, if we can measure its flow, then we can try to compare with theory to extract this eta by S, or kinematic viscosity, or shear viscosity to entropy density values. So there is a way to measure the flow. It is given by a quantity called V2, which is related to how the azimuthal angular distribution of particles are. I will not go into the technical details. So I'll just say that this is a measure of the flow of the system. And flow has been measured as a function of momentum of these particles for a wide class of particles. Now, so one such measurements are shown on the top left-hand side for protons, for pions, omega and phi. Purposefully, the plots has been made in such a manner that protons and pions have UD quark carrying hadrons, whereas omega and phi are heavier strange quark carrying hadron. SS bar and SSS are the quark constituents. Both are showing a large amount of flow, and the pattern for mesons, which are in red symbols, are similar, and the patterns for baryons, the 3 quark carrying objects, are similar, which are in blue. So what one did is divided this flow by the number of constituent quarks. Remember, baryons, as I mentioned in the earlier slides, are 3 quark carrying particles, and mesons are a quark and antiquark. So NQ for them is 2, for baryons it is 3. If we plot that quantity in the y-axis, and x-axis is a sort of energy divided by, again, the number of constituent quarks, you see everything falls more or less on one line. What I mean by this, there are particles like pions which have mass only 140 MeV, to nuclei which have much heavier masses. There are neutral particles, there are strange quark carrying particles, there are heavier nuclei, everything, different kind of charges. Some are mesons, some are baryons. So irrespective of their mass, the charge, the particle type, the way they interact, everything falls on one line. So what could be the origin of this? What other that this flow that we are measuring are actually flow of the constituent quarks and gluons. It reflects the flow of quark-gluon plasma. And subsequent interactions have minimal role in disturbing that flow pattern. So this is considered as an evidence of flow of patterns of quarks and gluons. Wide variety of particles, when scaled by the number of constituent quarks, flow follows a scaling. So if we have measured the flow of quark and gluons, now we can proceed to obtain its viscosity. So how does that one does that? So on the left-hand side is an energy momentum conservation equation. So one tries to solve this equation for the system, which we are produced in the laboratory with certain initial conditions, final conditions, equation of states, and eta by S, the viscosity to entropy density as a parameter. So x-axis is flow, y-axis is the momentum, the measurements are in blue. The equations are, hydrodynamic equations are solved without any eta by S. This is ideal case. This is what one would have expected for our system. Then one dials up the eta by S to 1 by 4 pi. As is expected, flow should reduce as viscosity increases, and that's what happens, it reduces. Then you go to 2 by 4 pi, 3 by 4 pi, and what you find is the data lies somewhere between 1 by 4 pi to 2 by 4 pi. This 1 by 4 pi being sort of a traditional lower bound a fluid can have, eta by S. So you can see the fluid that we produced, the one consisting of quarks and gluons, which all of us are made up of, has eta by S very close to this 1 by 4 pi. Compared to all other known fluids, which is shown on the right-hand side, they are much lower. A recent calculation which came out in Nature Physics on the lower right-hand side shows a comparison of this eta by S with water and helium, and it is the lowest so far known eta by S in among the fluids, and hence the term perfect fluid got attached to the system of quark and gluons. Now let me come to the other part of the talk about vertical fluid. Now this is based on measurements done both at Relativistic Heavy Ion Collider and the Large Hadron Collider in these two publications. What I will try to show is spin orbital angular momentum interactions in this QCD matter. Why it is interesting, you all may be familiar that spin orbital angular momentum interactions are something which plays very important role across the field of physics. In atomic physics, as indicated on the left-hand side plot, shell structures in the nuclear physics or spintronics and associated areas in material science. So we wanted to see if such interactions exist in this relativistic QCD matter, and if it exists, can we measure it? So first thing, what is the source of the large orbital angular momentum? So let me discuss that in this slide. Now, two nuclei are coming from opposite direction, and if they are not colliding head-on, that means the impact parameter is non-zero. Impact parameter is the center, perpendicular distance between the center of the two nuclei. If that are not zero, then the two nuclei will impart a torque to the system, and that would lead to large angular momentum. It would also lead to large magnetic fields, which I'm not going to discuss in this talk because the spectator, the uninteracted part of this nuclei are charged protons. They are moving away in relativistic speed, and they can give large magnetic field. But you will get large angular momentum, which is a conserved quantity for strong interactions. Initial set of calculations for a realistic system like gold-on-gold collisions at relativistic heavy ion collider is shown on the right-hand side. Angular momentum in h bar is plotted in y-axis. This is the impact parameter of the collision, and you can see that the angular momentum values can reach about 80,000 h bars. That's a huge angular momentum which is imparted to the system. For head-on collision, the torque imparted is less, so the angular momentum are small, and very peripheral collisions, it is also less, and hence this distribution. Only in mid-impact parameter collisions, they are very large, and this has a typical distribution as shown here. So we have large angular momentum. We have spin-carrying particles. For example, vector mesons like a K-star has spin 1. So we can try to measure spin orbital angular momentum interactions. Now for this one, how to measure it? What is that signature, and how do we extract it? So in 1970s, just following simple quantum mechanics, one can write down the angular distribution, theta and phi are the angles, angular distribution of decay products of this particle K star. This particle K star decays into a kaon and a pion. The angular distribution can be written mathematically following quantum mechanics as given in this expression. Just I will tell you that this rho is a spin density matrix. It's a 3x3 matrix. M are the decay amplitudes, and lambdas are the helicities. Now this theta, the angle that you see, has to be calculated in a particular frame with respect to some quantization axis. And let me just quickly explain what that is. So we have a K star, which is a vector meson. We go to its rest frame. In the rest frame, the kaon and the pion, the decay daughters, are back to back. Okay. Now, we look at the plane subtended by the beam and the momentum of the K star. The perpendicular to this plane is the quantization axis. The angle made by this any one of the decay daughters with respect to this quantization axis is what I call theta. One could define another plane, the beam axis and the impact parameter. Perpendicular to that is the quantization axis. And you look at the angle made by the decay daughter with respect to the quantization axis in the rest frame. That's the angle. And then you can get this expression. It is given in this 1970s paper of the angular distribution, just following quantum mechanics. You can write then the angular distribution in spherical harmonics. You could integrate it over the azimuthal angle. And finally, using some symmetries, you can arrive at an expression which is given on the bottom. What is rho 0, 0? You have a spin density matrix. So it is one of the diagonal elements. See, the vector meson can be in spin state 0, 1, or -1. So rho 0, 0 essentially tells what is the probability of finding the vector mesons in spin state 0. Ideally, all the three states are equally probable, 1/3, 1/3, 1/3. Okay. So if there is no spin orbital angular momentum interaction, then rho 0, 0 will be 1/3. What is the probability to find a set of K star in a box where the spins, it is in spin state 0? So it is 1/3. If I substitute 1/3 here, then you can find that the cos theta square term vanishes. So it is basically the angular distribution is a constant. If there is spin orbital angular momentum interaction, spins are aligned preferentially, the rho 0, 0 will deviate from 1/3. So the angular distribution will not be flat. And using the angular distribution, one can actually obtain this rho 0, 0 values experimentally. This is what is shown pictorially in this plot. Just to tell you what we expect experimentally, you look at the dn d cos theta star as a function of cos theta star. If there is no spin orbital angular momentum interaction, rho 0, 0 is 1/3. All spins are equally probable. You'll get a distribution like the red line. If there is alignment of spin, the angular distribution will not be flat. So that is what we set out and tried to measure. So I will first show you some results from the Large Hadron Collider at Alice experiment. Again, y-axis is the dn d cos theta star. This is the counts of particles as a function of cos theta star. What is theta star? It is the angle made by the decay daughter with respect to quantization axis. You can see for lead-lead collisions, for two different frames of reference, these are not flat. And so now I come back to my reference system, proton-proton collisions, where there's this large angular momentum is not there, it is flat. No spin alignment. And if I take particles which are spin 0, like K0 short, which decays to pi plus pi minus, it is also flat. So experimentally, we are able, of course, the errors are large. This year data will make the precisions better. Within this uncertainties, it is a 3 sigma effect that the distributions are not flat. Now I can use this expression which I showed here to fit these distributions to extract rho 0, 0. Okay, and that is what is plotted here. Rho 0, 0, remember rho 0, 0, 1/3 means no spin alignment. There is no spin orbit angular momentum interactions, and the data rho 0, 0 in the y-axis, the momentum of the vector meson in the x-axis, and you can see deviations from 1/3 for both kinds of reference planes. For proton-proton collisions where we do not have large angular momentum, it is 1/3. within the uncertainties. For particles which are spin zero, it is also 1/3. So we observed spin orbital angular momentum effects at 3 sigma level in heavy ion collisions. We went on to also measure those in a similar principle for spin half particles like lambda. And one can obtain from the angular distribution the polarization values. The polarization values in percentage are plotted in this middle plot in the y-axis as a function of the center of mass energy of the collisions, and at lower energies they were found to be non-zero, significantly non-zero. If we assume that these polarizations origins are due to vorticity of the fluid entirely, and the system is a thermal system, then one can obtain the vorticity through the measured polarization by the expression which is given on the left-hand side. And if one uses that, one gets vorticity of the order of 10 to the power 21 per second, rotations per second. And hence the idea that it is the most vertical fluid that is observed in nature. Just to give you a perspective on vorticity, there are many kinds which you have come across, like on a coffee or in the rivers or the cyclone. This is actually funny, which hit nicer a few years back. So all these have vorticities of the order of 10 to the power 3 per second. What we find, if we convert all these polarization to the vorticity, it would be of the order of 10 to the power 21 per second. So that is how the vertical fluid aspect came. So let me, on the last few slides, tell about the phase diagram of strong interactions and why it is important. So on the left-hand side is the phase diagram of water. Okay, pressure versus temperature, and there are 3 broad phases: solid, liquid, and vapor. And this is one of the most widely studied phase diagrams in science, and one which is very precisely known. The underlying interactions is electromagnetic, one of the 4 basic interactions in nature. It has been suggested that we could also have our phase diagram where the underlying interaction of the system is strong interactions. And one such possibility was laid down by this year's Nobel laureate in this physics letter B, that there would be 2 phases, one where quark and gluons are confined, which is phase 1, in this density versus temperature, and second is where the quark and gluon plasma exist. Subsequently, over the years, it has become more activities have led to a rich phase diagram. So it would look something like this. Y-axis is temperature, x-axis is baryon chemical potential. Why we plot it in this way? Because these are experimentally accessible quantities in some way, and hence this is sort of an possible experimentally realizable phase diagram. One could plot it as a function of pressure versus temperature, but this is how it can be experimentally realized. For example, by changing the collision energy, you can change the x and y axis and thereby have access to this phase diagram experimentally. Now, what it shows, remember the previous phase diagram, it has a confined state of hadrons, deconfined state of quark and gluons, but it is also very rich. For example, at small baryonic chemical potential. What is baryonic chemical potential? It is just the energy which is needed to put a baryon in a system or remove a baryon from a system. Now, at small baryonic chemical potential, it's expected to be a crossover. There is no sort of a defined phase transition like first order or second order. It's a smooth transition, something like ionization. At large baryonic chemical potential, one expects it to be first order. And the point where the first order phase transition ends is the white point there, and it is called as the critical point. Okay, so you can see that critical point holds a landmark position on this phase diagram. On the left of it is crossover, on the right of it is first order, above it is quark-gluon plasma, below it is the confined hadron, hadronic matter. So if one gets hold of this point, then the phase diagram will become a reality. And then perhaps it will end up in textbooks. That is the sort of interest which we have to locate this point. Plus, the signatures are amplified at this point. Hence, it may be easier to locate a critical point if the system passes by it compared to other ways of putting the phase diagram into reality. So that is why this search of critical point happens. The background picture is about critical opalescence. This is transparent liquid turning milky due to density fluctuations, which has been studied in late 1800 widely. A similar phenomena is what we are looking for. The challenge being we have a very short-lived system and we have to establish the observables and compare to theory. So what are the observables? Something which is related to the correlation length of the system, because at critical point, the correlations lengths should ideally diverge for a static system, but for an infinite static system. But our system has finite size and time effects, so the correlation lengths will attain maximum values. What are the quantities we measure in experiment which can be related to correlation length or to a susceptibility, because susceptibilities also will peak if we hit the critical point. The quantities are moments of multiplicity distribution of quantities such as net proton. What is net proton? This is number of protons produced in a collision minus the number of antiprotons related to net baryons, which are conserved quantities in strong interactions. So we calculate event by event difference in number of protons and antiprotons and the moments of this distribution. First moment is mean, second moment variance, third moment skewness, and fourth moment is kurtosis. These are related to quantities which are sensitive to correlation length and susceptibilities. And we try to study these quantities. So the connections which has been made to these observables can be found in these papers which I have listed here. So what is the signature? One specific calculation which is published in this paper in PRL tells that if you look at kurtosis, fourth order fluctuations, as a function of collision energy, one should see such non-monotonic variations. That would be a signature of existence of critical point. On the right-hand side is our measurements, and you can see there are indications of a non-monotonic variation. Of course, with the large error bars, it is only at 3 sigma level. We have already collected a factor, maybe 10 to 100 times more data at different energies to reduce these error bars. But the existing data does show a 3 sigma level non-monotonic variations, and experiments, precision measurements are undergoing to see if this exists. If it exists, then the explanation, only possible explanation so far is that there would be a critical point the system is passing through in the temperature versus baryonic chemical potential phase diagram through a critical point. So these are exciting times for heavy ion collisions. So I started with Frank Wilczek's note. Recently in 2021, after we published this paper, he came up with an article in, I think, Wall Street Journal, saying that experimenters at Brookhaven have reported hints of just such behavior, this non-monotonic behavior that I talked. They are now analyzing a much bigger data set to nail it down or not. If all goes well, they will have demonstrated that deep ideas invented to understand problems in physical chemistry, thermal engineering continue to be useful far beyond their down-to-earth origins. So we are eagerly waiting and analyzing the data to see if the signatures of critical point exists or it vanishes. Either way, it is beneficial. Even if there is no critical point, we will be knowing that maybe the entire phase diagram is a crossover. So let me summarize. What I have discussed is we have seen this QCD phase transition, and we have created a deconfined state of quarks and gluons. We have reached temperatures of the order of 10 to the power 12 Kelvin, which melts all matter into its fundamental constituents. We were able to study some of its properties, other like diffusion, conductivity are underway. We find that it's close to perfect fluid and has high degree of vorticity. We are trying to lay down the phase diagram of strong interactions. Some exciting results on critical point has come out from the existing data. A high statistic data set has been taken to see if the signature stays. We are sort of studying the emergent properties of QCD matter. I will end with this note to younger colleagues to join these mega science projects. And this is very nicely put in this picture, which was part of Big Gun Samagam, which happened in India. So if actually the some of the projects which is funded by Government of India are shown on the lower side. If you want to know about universe of the order of time scale 10 to the power minus 43 seconds, you could join INO. If you are trying to understand the universe evolution in 10 to the power minus 32 to minus microsecond old, then experiments at CERN and RIC, which I discussed, are ideal. If you want to know a few minutes old universe and how nuclei are formed, you could join the FAIR facility, which is coming up in GSI. If you are interested to know how the first stars are formed, then you could perhaps join the square kilometer array. And if you are interested in a 500 million years old universe, you could join the 30-meter telescope project, where India has large participation. If you want to understand a billion-year-old universe where there was thermonuclear fusions and want to solve the power problem, then you could join ITER. And if you are interested in few billions of years old universe where black holes and neutron stars collided and gave gravitational wave, you could join the LIGO India effort, which is coming up. So please come and join these mega science efforts. Thank you very much.
Thank you, Professor Mohanty. Let us first, you please unmute yourself and thank Professor Mohanty for this wonderful talk, and then we will take questions one by one.
Yeah, thank you, Professor Mohanty, for a wonderful talk. I am really glad that we had such a high-level talk at IISER Bhopal. I mean, not being from this area, also I enjoyed that talk thoroughly, and people in the audience will definitely resonate with me. So as Navamita said, now we'll take up question answers. People can raise their hand, and then we can unmute them and they can start. So first, I see Suvankar's hand raised. Suvankar, can you please go ahead?
Hello. Thank you for this wonderful talk. I have a very naive question. Usually, if I understand correctly, these QGP, they are charged fluids. So they have some, I mean, even at the first order, there are other transport coefficients like charge diffusion in the parity even sector. And also, I think these are parity, I mean, these fluids are parity odd also. So so you get some coefficients in the parity odd sectors also. So in these experiments, in this RIC experiment or maybe in LHC experiment, is it possible to kind of calculate different transport coefficients, all the transport coefficients associated to this QGP matter? or you can, for example, you have calculated eta or vorticity omega. In that way, is it possible to calculate all other transports also?
Yeah, there are attempts to calculate, for example, bulk viscosities, attempts to calculate diffusion, drag and diffusion coefficients. And there are also attempts to look at these parity odd effects. They are all possible. Of course, our biggest challenge is short-lived system with lot of background. So the challenge is to control the background to extract these features.
Yes. Oh, thank you.
Thank you.
Deepan?
Am I audible?
Yeah.
Yes, sir. In the spin orbit coupling, if we include Thomas precession, how will the scattering calculation change? The rho not and
Yeah. I now exactly don't remember, but there is a paper which tries to explain our measurements using what you said, Thomas precision. I can send you the reference. If you drop me an email, I can send you that paper. It's in Physics Letters B. I'm forgetting the year and the volume, but you can take a look at it.
Okay, thank you, sir. And sir, one more question. In the quark in the quark gluon plasma, if we have FLRW cosmology, which has a time dependent metric, in that case, how will the different parameters change, and could there be any kind of relationship with the primordial matter?
That is beyond my scope. If anybody from the audience would like to say, yeah, but yeah, that I would not be able to say.
Thank you, sir.
Ritam?
Vedang, for this wonderful talk. So I just wanted that you people found out the hadronic.
Ritam, we couldn't hear you. Is it me?
Okay. Hello.
Please,
Yeah.
please speak.
Hello. Can you hear me? Hello.
Yes.
Okay. So my question was, you have found out such high vorticity. So when you are doing the hydrodynamics, like del mu t mu nu equal to 0. So have you included such high vorticity there, or is there any change you expect considering this high vorticity matter?
Yes. So there is a huge amount of effort to include in this 3+1D hydrodynamics the spin part, and there are different ways to include it. My colleague here, Amresh Jaiswal, is trying to develop that area of how to include spin effects into hydrodynamics. It's an evolving field. So you may want to discuss with him. He is an expert working with people, colleagues, I think in Poland group and Germany group. Yeah, so.
Okay, I'll do that. Thank you.
Yes, Rajiv?
Bedanga, you began by a quote from Wilczek.
Professor Gaba, you are muted.
Now?
Yes.
Bedanga, you started by showing a quote from Wilczek in which there were two different levels. One which was a qualitative explanation, which is what you seem to have concentrated. My question is, at the second more rigorous level, to make a connection with QCD, the fundamental QCD, is any of what you have really shown possibly now related to QCD?
Yeah, so what I showed, the critical point studies would be one I didn't show any comparison to or expectations from lattice here. Lattice also at the moment up to about 200 MeV in mu B has ruled out the existence of critical point. The connection would come through this observable as you and Saurendu had worked on. The susceptibilities can be calculated from QCD, and which is on the lower side, right hand side of the expressions, the susceptibilities, various order, baryon number, and the left hand side is what we will be measuring in experiment. So that is the will allow the connection. But yeah.
No, I was really referring to either the perfect fluid or the vorticity.
Yeah. So there it is sort of for the perfect fluid, there is indirectly QCD input in terms of the equation of state, which goes into the calculations. Otherwise, it is a relativist, as you know, relativistic hydrodynamics. The input is the equation of state from lattice.
Okay, thank you.
So, Professor Mohanty, we have a student of class 11 in the audience. He has put some questions in the chat box. I will try to unmute him also in case he wants to speak out and ask this question by himself. But he has some questions like, is space flat or curved? You can see those questions in the chat box.
Yeah, space, it is curved, you know, it was first demonstrated by Arthur Eddington, I guess. He actually showed that light in presence of mass bends. How did the universe begin? Well, the model which we know is the Big Bang model. So far, the whatever best we know, and it has predicted certain signatures, which we have seen. Three such I mentioned. What happened during the Big Bang? You mean before that? There are some speculations regarding it, but I am not an expert in that topic to discuss about that aspect. Where was the Big Bang located? Okay. Well, yeah, it is. I guess we think that that is where the system sort of, universe sort of started, all aspects of it. So that is all I can say. Others, of course, anyone in the audience can also speak. Is there a center of the universe? Well, I can say that certainly we are not in the center of the universe. We are not even the center of our galaxy. We are quite far away. The center of our galaxy is a black hole. So, and the universe is currently expanding. Okay, anybody? Yeah, I think maybe Rajiv wants to say.
There is definitely no center of the universe. Everybody is receding from everybody else. So there is no center.
It's like two dots on a balloon. If
yeah. And also there is no question of locating Big Bang anywhere because the entire space-time had collapsed. So there is no question of locating it. It just is a singularity.
So there are some more questions in the chat box. Shall I read out or?
I will read it then. Is it possible to attain temperature 10 to the power 32 Kelvin? You want to go to closer and closer to Planck's scale. At the moment, none of these accelerators can do that. The energies maybe from cosmic particles can take you a little higher. Otherwise, there is no facilities to reach directly to those temperatures. And will we be able to unify all fundamental forces in this temperature. In the standard model, gravitation, well, interaction is not part of it. There are people working in attempting to unify it, but yeah, put it inside the standard model. So, yeah.
Yes, the next question is again from a class 11 student, says which fluid is more fluid, has more fluidity?
So far, quark-gluon plasma seems to have the least eta bias, the kinematic viscosity, not the eta per se, but eta divided by the density.
Yeah, so next question is, I think, from Kritika Sarkar. Is it true that there are universes within a universe? Universes within a universe.
Okay. Well, there are some ideas in that context, but nothing sort of, there are signatures or proofs of it. How is the concept of fluid related to the QCD? You see, it is by the nature of interactions. A weakly interacting system, if we would have found, then it would be a natural way to put it as a gas. A strongly interacting system is a sort of like a liquid-like system.
Yeah, so I think that's all the questions we have in the chat box. And I don't see any hand raised. Vandana, are there any questions on the YouTube?
No, there are no questions in the YouTube. Okay. So, but I would just like to add, Bedang, really a very, very nice talk. And it's nice that you also tied up with the opportunities for the younger students on that. Yeah.
Thank you. Thank you for giving this chance to talk.
No, so I think we should thank you here for taking up time to give this wonderful lecture. And we are really, right now, we are overwhelmed with such a nice lecture. Thank you so much, Professor Mohanty. And I should also thank Professor Vanna and Professor Rajiv Gavai and our own Dr. Suvankar for arranging this talk, which was very nice Saturday evening, I think, for all of us. So with this, I think we can wrap up the week and go for a weekend.
Thank you to ISER Bhopal once again for arranging it. Thank you, and everybody take care. Stay safe.
Yeah. Thank you. Thank you. Stay safe.
Bye.
Bye-bye.
Bye-bye.